Hey everyone, welcome to the Intro to IPLD session of the Filecoin Club. Today we're joined by Daniel Martí, who's a software engineer at Protocol Labs, to tell you all about IPLD, how it all works, and why it's useful. So Daniel, if you are ready, feel free to kick off.
Great, thank you. So I'm going to be talking about IPLD, also known as interplanetary linked data. And I'm going to be throwing out a lot of concepts and ideas here. So what I'm going to do is I'm going to pause twice during the talk for questions. So if you have questions, I believe you can write them in the chat or in the Slack or in the Discord, and then we're going to get through those during two pauses later on. So the agenda today is, first we're going to talk about why we need IPLD, what is it and why it exists. Then we're going to talk about the relationship with IPFS, because IPFS is the better known project, is the original project. Then we're going to talk about some concepts such as graphs and linked data, Merkle DAGs and their roots. And we're going to talk about why links are at the heart of this whole concept. And finally, we're going to talk about beyond files with IPLD. So what is the data model? What are codecs? And then the big stuff that you can build on top of all this, such as distributed data structures. So first, why IPLD? So IPLD, you can think of it as the data layer for content-addressed systems. And what we mean by content-addressed systems here is essentially a system where you can talk about data given their content, i.e. with hashes. You can think of Git, you can think of blockchains, you can think of IPFS. And the question is, can we extract reusable data layers from IPFS such that you can build any system on these concepts, without being tied to IPFS and files? Another way to think about this is that if you were to build Git today, it should take you hours. It shouldn't take you days, because you already have all those building blocks. So IPLD as leverage aims to answer a bunch of questions. And the main ones are, how can we scale the size and complexity of the data that you share peer-to-peer? I can give you a bunch of data, a blob of data, and that's fine. But you very easily get into sizes that are too large to share as a single piece. You want chunking. You also want to be able to verify data and so on. Another question is, can we unify disparate content addressed formats and link between them? For example, we talked about blockchains and Git, but also IPFS, and all of these use the same concepts. All of these refer to data by their content and their hashes, but they're all kind of their own silos of data. I cannot really have, for example, a Git repo that mentions blockchain hashes as if they were Git commits. They don't talk to each other that way. And another question we want to answer is, can we build distributed data systems such that you can interact with them easily, such as you would with, for example, a SQL database, while still taking advantage of all the primitives of content addressable systems? Now, IPLD aims to answer those questions, but these questions are tricky. So we're going to get into those in a little bit. Now, in terms of the relationship between IPFS and IPLD, it depends on your context, where you're coming from. If you're coming from IPFS, IPFS is a way to store directories and files, right? So you're talking about files just being raw blobs of data. You don't know what's contained in them. It's just bytes. So you can think of IPLD as the data layer of IPFS. So IPFS has its own metadata, and it can also store files. So IPLD is how you could describe that structure. Another way to look at it from the other end is that if you start using IPLD and then you look at IPFS, IPFS is like a block store for IPLD, because IPLD, it stores at the lowest level data in blocks, which is just raw bytes. And you could put those blocks in IPFS as files. So in that way, IPFS could be a storage for IPLD. So like we said, IPFS at its core, it's a collection of binary blobs of data. You can call them files or blocks. It's essentially the same thing. And they associate between one another with content identifiers, and we call those CIDs. And CIDs are just a form of linking. Whenever I say link or CID, it's practically the same thing here. Now, if you store a very small file in IPFS, that will most likely get stored as a single blob, as a single block. But if you have large files, you start getting into problems of having that whole file as a single blob is not a good idea. Because if you only want a small piece of it, then you have to download the whole thing. Or for example, internet connections are not reliable. So if I try to download a whole gigabyte of data all at once, that might fail, and I might have to start over. So what happens with IPFS, for example, is it likes to chunk things up into reasonable sizes. And you can think of reasonable as hundreds of kilobytes, a few megabytes, that kind of thing. And directories are pretty much the same thing. They also use a form of chunking, but essentially their content is not raw data. It's just links to files or links to other directories. So in a way, it's fairly similar to a file system tree. Now, here's an example of how a file in IPFS might look like. And they're called UnixFS files because they mimic a file system, at least in a Unixy system, operating system. So in here, we have a file that has been chunked up, but we actually have up to 6 CIDs here. So we have the root CID. So if I tell you here's my file, I would give you the root CID, but the root CID doesn't contain the data directly. It simply points to other things. So in this case, there's 2 levels of CIDs. And then when they actually point to the chunks of data, notice that because my file actually overlaps with some data, it reuses, it has duplicate data in it, you can actually end up chunking your data so that you reuse the same chunks in different places. So for example, if I have a file that's like 10,000 A characters, that might be a single block, just repeated many times through links. And now we're going to talk about fundamental concepts. So I've been talking about trees and Merkle DAGs. So a DAG is just another way of saying a tree. You can think of it that way. The point here is that it's directed. So as a graph, every edge has a direction. And the idea here is that the edges are hashes, right? They're links. So you can only hash in one direction. If A hashes if A is the hash of the content of B, you cannot have it both ways, because then that would be like a cycle. And hashes, you need to know what the content is before you have the hash itself. And you cannot have cycles for the same reason. Once you have a cycle, it's sort of impossible to calculate any hash because you will never have all the data that you need for hashing. And this idea of DAGs, or what you can call Merkle DAGs based on hashes, is a pretty old idea. It's from the 70s, but the sort of change that you can think of here is that the nodes that are not leaf nodes don't need to just be hashes. They can also contain data of their own, and we're going to give some examples in a little bit. So the best example here is Git. Most developers are familiar with Git, and Git is a Merkle DAG in a way. So you can think of the raw blobs of bytes at the bottom layer, the leaves, and these could be, for example, files. And on top of them, you have directories, and Git calls them trees, but you can think of them as directories like in IPFS. But then to make those trees and those committed files useful, you need to expose them and use them in some way. And the way they are used is with commit hashes. So you have these 3 layers, right? And you can think of, for example, the top level, the commit, as a root node that links to maybe the parent commit to have a history, as in a sort of blockchain of the data that you've had over time. But they also point downwards towards trees that contain blobs, that contain files. And notice that, for example, if I have a commit, it's not just a hash of other hashes. It also has data of its own. A commit might have an author name, an author email, it might have a timestamp, but on top of those things, it also has a hash, which is the combination of the hashes of other nodes in this graph, in this tree. So here's another question that we need to answer, which is hashes are great because they give you a lot of nice properties. But the problem with hashes is that they change if the data changes, right? So if you have these immutable Merkle DAGs, how do you actually change them? Because in the real world, if you have data structures, to make them useful, unless they're like immutable forever, you need to mutate them, right? So you can actually mutate them. So what you essentially end up doing is, for example, in this case, we start with a tree, and we want to add some nodes, we want to delete some others, we want to modify some others. So essentially what you do is you do your operations, and then anytime you go up to actually apply those changes, you go up to the parent, its hash might change. For example, if one of its children got deleted, its hash will change. And then you will have to replace the parent. So you might end up with a new tree that might reuse some of the subtrees if those subtrees were not modified. But if any of its nested children gets changed, then the root node will also need to be changed, the root hash. And then another nice property of this system is that, for example, if you have a very, very, very large data structure and you only change one tiny piece, other people that want to get that update only need to get those nodes that updated, that got changed. If 99% of the structure is exactly the same, they already have all those hashes stored locally, so they don't need to re-download the same stuff again. Now, one concept that's important here is the roots, because we've talked a lot about hashes, but you need a root to start from, right? What you could think of as a pointer in memory when you write programs. So in this case, in Git, you might start with a root being your first commit, and the first commit doesn't have a parent commit because it's your first commit. It only points downward to its data. And what if you say, okay, I'm going to do a second commit? So this second commit will link to the first commit as its parent. So that's sort of the blockchainy concept of you have a chain of commits. And all the data, all the files, even if they don't exist in the current version of your software, if they're still linked to from one of the parent commits, one of the past commits, they will still be reachable. And notice that in here, we added two files, two blobs on the left, but the current directory still has all the same files as before, so the same blobs are reused. So this concept applied to Git means that in a repo, in a Git repository, if you add a bunch of files but leave the others intact, the files that are left intact do not take up more space because their hashes haven't changed at all. And what if you want to remove two files from the latest version? So you would essentially do the same thing. You would stop linking to a couple of files, but they would still be there if they're linked to from a previous commit. And what if you want to move some files under another subdirectory? So you would essentially have two levels of trees. You can think of this as a way of chunking things up as well. So you would have the top level tree, that's a directory with a bunch of files and a subdirectory, and that subdirectory is another tree that links to other files. And what you could do is, what if you only care about the latest commit? You only care about the latest version. You could cut the edge that goes from the current commit to its parent. And once you cut that, that edge, you can prune and remove all the data that's old and no longer useful. So in this case, any trees and any blobs, any files that are not reachable from the current version will simply get pruned away. They will be removed. So we've talked a lot about the benefits and the properties of the system, but I want to get into links because links are at the heart of this whole concept. Now, CIDs are a little bit special because they're not just a hash. They also contain metadata that makes them more universally useful. Because the problem with a hash is if I just give you, for example, a 32-byte hash, you know that refers to some data, but you don't know anything else about it. You don't know what hash algorithm was used. You don't know what the data behind that is meant to be. You don't know what the data is encoded as. So CIDs contain this information themselves. And they start with something called a CID version. And you can think of these prefixes as sort of magic numbers. So for example, if I store a PDF file, its first few bytes will be some unique, globally unique bytes that say, hey, I'm a PDF file version 1.1. And if you look at a JPEG or a PNG file, they also start with magic bytes like that. So CIDs are sort of similar. They begin with a specific set of bits that say, hey, I'm a CID version 1. And then they continue with a multi-codec. And a multi-codec is another globally unique identifier from a multi-codec table. And a multi-codec table is just something that that we defined. It's arbitrary, but as long as everybody understands what the same numbers mean, it works. And for example, in this particular case, the 70 hexadecimal number tells you that the data pointed to by the CID is encoded in DACPB. And that's just a codec like JSON. And we're going to talk about those in a second. And another prefix that's there is what hash function was used to obtain this hash. So in this case, it was SHA-256. And then finally, the hash itself, which is the length of the hash and the bytes of the hash. And all of those are important because you want hashes to be deterministic, and you want people to be able to understand what's behind the CID. and how to use it and how to reconstruct it. So if I know, for example, if I have the raw data, the bytes behind the CID, and I know what hash algorithm was used, I can reconstruct the same CID with the same hash algorithm, in theory, as long as everybody's done things correctly. So we've talked about CIDs and what makes them different from regular hashes, but getting a little bit more into specifics, I mentioned DACPB as the multi-codec that's being used here, and I mentioned JSON as another example. But something that you should remember here is that data formats like JSON and CBOR and protobuf, they're fine, but IPLD sort of uses modified versions of those codecs. You can think them of building on top of those codecs, because IPLD itself needs to store other kinds of data like links. So we bring these formats and we call them multi-codecs. And I'm going to give a couple of examples in a second. And these CIDs can also be used to link to data that's outside of the IPLD realm, if you want to call it that. So for example, you could have a CID where the multi-codec for the format that the data is behind that link might be Git. So you could point to a Git commit using the right hash function and using the Git multi-codec. And then if I see that link, I know that what's behind there is a Git blob, a blob of Git data. It might be a commit, it might be a tree. So it's useful because you can link from the quote-unquote pure IPLD world into other places that also use hash systems and content addressable systems, but that don't directly speak the same language. But something to note is that once you enter into that realm, they don't have CIDs. They usually don't have IPLD links. So you can link to those worlds as a sort of read-only view of their data, but you cannot link back, at least not with places like Git. Now I'm going to do the first pause for questions.
Yeah, I think we've had a couple, but Discordian in chat is kind of very helpful on all these sessions. But yeah, the main question was, what's the incentive to use IPLD?
So the incentive is, you could have multiple incentives. I think the simplest one might be, I want to have data that I want to hash in a stable way over time. So one example is Git, right? So suppose you want to publish software and you give somebody else a commit and you tell them, as long as this commit is the same, the code will be the same. If the commit hash changes, you know somebody has messed with the code. So this is one of the properties that IPLD gives you. If you want to have data and be able to tell people, hey, this data has, is exactly what I'm telling you it is and hasn't been modified, you can use something like IPLD. You could build it yourself with hashes, but usually a hash function takes in bytes, right? So when it takes in bytes, that's not structured data, it's just raw bytes. And the point of IPLD is that it gives you the data model, it gives you the tools to structure your data so that you can do two things at once. One is use the data as a structured something, be it a tree, be it a Git repo, be it a graph of your friends. But you can also have hashes and tell people what this data is just by its content. And the other use case would be building distributed systems. And I'm going to give an example in a little bit.
Awesome. Thank you very much. I think that's all the questions for now.
Yeah, and I like what Discordian said, which is IPLD gives us our precious CIDs. And that is a very good point. CIDs are like the main benefit from all this. If you want to have one takeaway from this whole talk, is how important links are in IPLD. Because IPFS does have links, but the links only point to like other files or other directories or other raw data. The point of IPLD is that they point to something that's more useful. They point to something that's structured and it tells you how to use that data. So expanding a little bit on the relationship between IPLD and IPFS, we've said that IPFS only stores files and directories. And the way it does that is with a codec called DACPB. And DACPB is just what we've called a dedicated protobuf schema. It's a specific protobuf format. And all it does really is store some raw data, be it, for example, a file itself or a chunk of bytes for a file. And it also contains a list of links to other things. So you could think of, for example, a directory as a DACPV block that contains very little to basically no data, and instead contains links to other blocks. And IPFS additionally has an encoding for the data that's stored internally in those DACPV blocks. And this is called UnixFS. And this is what stores the metadata about files and directories. And I'm not an expert at IPFS, so I might have said some of this wrong. So if anybody in chat has corrections, please say so. But beyond file data, because IPFS, like we said, is only raw bytes, what else do we need if you want to build complex and large data structures with IPLD blocks without having to make everything a file? Because you could make everything a file, but like we said before, once you turn everything into raw bytes, you lose a lot of benefits. So IPLD defines a data model, and you could think of a data model as a sort of type system, or rather the basic types for a type system in a programming language. And the types that you have here are sort of the common denominator between most codecs. And it's actually pretty similar to JSON. You've got Booleans, you've got strings, you've got ints and floats, nulls, arrays, maps, but also bytes and links. And these are two that, for example, JSON doesn't have. And an IPLD block is just a way to encode that data into raw bytes, right? So you might think of it as similar to how you would store that data in memory. It's just that links and bytes are especially supported. So we have other encoding formats. We've talked about JSON. So JSON plus links and bytes is called DAG-JSON. And DAG here is directed as acyclic graph. It's just a way of saying DAG-JSON is JSON plus the extras needed for storing Merkle DAGs, for storing these trees of content addressable data. And DAG-CBOR is essentially the same, but for CBOR. And CBOR is an encoding format similar to JSON, but it's binary. So that makes it smaller and more efficient. And I believe it also has native support for bytes. So it's a little bit less clunky for those things. So here's an example. And these examples use JavaScript, but you could use any language that has support for IPLD, such as Go. So the data model includes these fundamental types for basically most codecs and programming languages, right? So here's some data with a string, an int, a Boolean, an array, but also a bunch of bytes and a link to some other data. And this link is a CID, like we said before. So if you want to encode it as DAG-JSON, it will look something like this. Now, it's worth noting that because we use hashes for these links, you want the data encoding to be deterministic. And this forces the codecs like DAG-JSON to be canonical. So for example, in this case, you can notice that the keys have been sorted alphabetically. So you have arrays at the top and string at the bottom. But also, to make it canonical, it wouldn't have any spaces between tokens. This has been indented and spaced for readability purposes, but the actual DAG-JSON would have no spaces around tokens. And you can also notice that bytes and links, they're sort of like this special funky object with just one key. And that's how DAG-JSON encodes these special data model types that the JSON encoding natively doesn't understand. And the point of this is that, for example, you could store a CID, a link, as a simple string. But when you were decoding that, if you just looked at the bytes encoded in JSON, how would you tell that that's a link or a string? There's no way to tell. So this special object with a single key is a way to signal, hey, I'm a link. And similarly for bytes, but with a bytes subkey. And here's another example, the same data, but in DAG-CBOR. Now, DAG-CBOR does have what's called a tag, i.e. a kind or a type for bytes, but it doesn't have anything for links. But because its tags are just numbers, so a tag is essentially, tag number 20, what follows is a string. Tag number 21, what follows is an integer. And I don't remember the exact numbers, but I'm just giving examples. So what you can essentially do with DAG CBOR is define an extra tag that's not part of the CBOR spec, but that you add on top of it. And that extra tag says what follows is a CID. And just as before, the actual DAG CBOR output is binary, it doesn't have spaces. So like we said, the encoding is deterministic. So what that means is that you can round trip this data through codecs and even different codecs. If you give me some data that's encoded in JSON, and then I decode it, encode it in DAG CBOR, and decode it again, the data will remain the same because the data model is a sound type system, right? It's strict about how the codecs need to preserve the data the same way it came in and will come out. And like we said before, in a content addressable world, you want the same data to have the same hash as long as it's encoded with the same codec. Because if you didn't have that, then different people with the same data would arrive at different CIDs, at different hashes, and then they wouldn't be able to share that data purely because of the hash being the same. If the hashes were different, they might assume that the data is different and then copy it instead of reusing it. So as a bit of a recap before I stop for questions again, the IPLD consists of a data layer for content addressed systems. And the data layer is just a way of saying how to understand the data and how to encode and decode it and how to link between those pieces of data. So it includes the data model, which is the basic types, the mechanisms for going back and forth between bytes and structured data, a way to address the data with CIDs like we explained, and then perhaps most importantly, the tools to use that structured data, because all that I've said so far is really interesting as a concept, but you need good libraries and good tools to be able to efficiently and easily use this concept at a large scale. And I'll give an example in the next few slides after the questions.
Awesome. We have 2 questions. What is a protobuf?
So protobuf is, at its core, it's an encoding, but it's also a schema language. So in protobuf, you can say, I want to define a struct with some fields, and this field is a string, and this other field is an integer. And then you can use that kind of like you would use JSON to, for example, expose APIs over HTTP, and then have people encode a request, and then you can encode a response back to them that follows the protobuf schema. The interesting bit about protobuf versus other encodings like JSON is that it uses a schema. So whereas JSON is just arbitrary data, and you can have objects, you can have arrays, protobuf has a schema, and the schema tells you exactly what format the data will be. I don't want to get too deep into that, but you can think of the IPLD data model, which also has schemas actually, is pretty similar to protobuf. It's just that its use case is somewhat different because protobuf is purely just about encoding and decoding data, and IPLD is also about linking content addressable systems.
Abraham said, is it kind of like XML? Or?
I would say XML is most like JSON. XML does also have schemas, I believe. Well, JSON also has schemas, technically. It's just that you can use both XML and JSON without any schema. You can just have arbitrary data encoded in those codecs, whereas protobuf is meant to be used with schemas pretty much always, I believe.
Okay, cool. And Smithy has asked, are there any starter guides or tutorials? I think they're referring to IPLD in more generally.
So I believe if you go to IPLD.io, it gives you like a visual overview of the project and why it exists, but it should also link to documentation with some examples in both JavaScript and Go.
Fantastic. I'll put that link in the chat for everyone. But yeah, I think that's all the questions for now. Thank you very much.
Cool. So I only have a few extra slides, and they talk about what I mentioned earlier, which is large and distributed data structures that you might build with IPLD. So persistent and immutable data structures are not new. If you look at languages like Scala, Clojure, Haskell, they have had something that translates almost directly to these concepts of distributed content addressable data structures. but they're not exactly the same. And the core point of all this is that you need good algorithms for building, traversing, and mutating these addressed data structures. And there are trade-offs at play here, because if you simply have mutable memory, if you want to modify, for example, one node in a graph, it's very easy. You just go and modify it. But once you have a content addressed tree, like we said before, the algorithms get a little bit trickier because, for example, if anything linked to that node, you need to make a copy and then walk up its parents to modify, to update those hashes. So there are some algorithms that are not rocket science, but they need to be implemented correctly and with the right trade-offs in mind so that they are efficient and easy to use. And these directional and acyclic graphs of immutable data can be challenging to wrangle, because you have to sort of change the way you think about your data a little bit to keep immutability in mind and hashing in mind. But once you are used to this kind of building your data structures, it does scale much better for some use cases, and you do get some benefits. And here's an example. Suppose that you have an array that wants to get very, very, very large. And I'm going to ignore the possibility of storing this in a single machine, because you can think of a single array being 1 terabyte or 1 petabyte. But let's start small. Let's say that a single block of data, so a single chunk of data, can only store 5 elements of this array. And the elements could be strings, could be ints. It doesn't really matter. We're just calling them elements here. So we start with just 1 block and 5 elements. So that single block is a chunk of data, is a block. So we can make a CID to it. We can choose whatever hash algorithm we want. And we can choose whatever encoding we want, like DAG-JSON. What if we want to add some extra items to this list? We can't add them to the same block because it doesn't fit. Like we said there's an arbitrary limit of 5 elements per block. So what you could do is add another level. So at the bottom level, what we can call height 1 is these are the leaves containing the data, containing the elements. And levels above compose those to sort of concatenate them into a single array. So you end up with 3 CIDs. The root CID at height 2 points to the other 2 CIDs at height 1. And then each of the height 1 blocks only contains up to 5 blocks, but the whole array, when you use it with IPLD, has 8 elements. And you can still use the root address of the height 2 block to refer to the whole array, because again, being a Merkle DAG, being a tree of hashes, if you have the root hash, you can rely on the content of everything that's under it to be stable and to be reliable, as long as you trust whoever gave you that hash. So here's another example. We can fit up to 25 elements with just 2 levels, right? Because you have the second level having 5 links to 5 leaf blocks, and each of the 5 leaf blocks has 5 elements. That's easy enough. What if you want to add another one? Well, you just keep on adding levels, right? This is exponential. So you could have a third height that links to the second height, and then this sort of tree can keep expanding up as needed. But once you got to like 3 or 4 levels, you could already store a lot of elements because it's a tree, it's exponential. Anytime you go up a level, it's a power of multiplication of how many elements you can have. And if you wanted to use this array in, for example, JavaScript code, here's some pseudocode. It doesn't actually work because getChildAt is left as an exercise for the reader, but you can think of the code looking something like this. If you actually wanted to use this array in, for example, a web app, what you would do is you would start at the root block and you would say, am I at the bottom? If I'm not at the bottom, I need to go down 1 level to recurse into myself. So I need to know what child to go into, left or right. And once I get there, I just iterate again. And once I'm at the bottom, I just simply get the element from this chunk that I'm looking at. And now these algorithms can get kind of finicky and complex depending on what your data structure looks like. But I'm sure you get the basic idea that you essentially use these data structures by traversing their trees, their DAGs. And that is it for me. Any more questions?
Awesome. Thank you very much, Daniel. Yeah, I'll just give it a couple of seconds in case people have more questions in the chat. But yeah, fantastic talk. Thank you very much for that. And just to remind people, upcoming we have next week is the building on IPFS talk. And I've sent the link in the chat for that. And the following week will be the intro to NFTs talk. So very much looking forward to those sessions and hoping to see all of you there as well. And if you haven't already, be sure to join the Encode Club Discord, which is where we post all the announcements about the upcoming hackathon, etc., and the upcoming events as well. Warp Forks just said that he thinks Protocol Labs is either hiring or supporting contracts to work on things in or near IPLD. So if anyone is interested in that, find someone there to reach out to. Awesome. And Will has asked, do you have any examples of projects that are utilizing IPLD?
So I think maybe the best example here might be Filecoin. So Filecoin is a blockchain. It's a blockchain project. And its blockchain stores some data, right? So each block in the chain stores some data and then links to the parent. And this data, it could be its own custom format. If you look at other blockchains like Bitcoin, they came about way before IPLD. So they don't reuse the same building blocks and the same concepts and libraries. But they do encode the data that they need in their blocks in their own way, custom way. But Filecoin, what they did is each of their blocks, it has some data encoded in what I think is DAG CBOR. So you can actually use IPLD to decode the Filecoin blockchain. And I believe the Filecoin project itself uses some of the same IPLD libraries to actually build and use those blocks. So I think any other blockchain that has been built recently could also use the same libraries, but you also have examples. You can also run into examples of projects that use IPLD for its properties, which are not directly blockchain. They might be interested in the property of deterministic encoding for hashing, for example. Or they might use other properties like the links being self-describing, which can be useful for many other things.
Fantastic. And Discordian's also put a link to the kind of Protocol Labs grants at the moment as well. So be sure to check those out, everyone. But yeah, looking forward to hopefully people utilizing this in the hackathon as well, which will be starting in October. And yeah, thanks again, Daniel, and everyone for attending today. The recording and slides will be going live tomorrow, so keep an eye out on the Discord for that as well. But yeah, have a great, oh, there's something else from Warpfoot. Awesome. Yeah. So yeah, everyone have a great evening or afternoon wherever you are. And yeah, see you next week.